Good morning everyone. So today we are going to discuss multiplexer. These are the subtopics that we are going to discuss. We will see what is a multiplexer. Then we will start with the basic version of multiplexer, which is a 2x1 mux multiplexer, and then we will extend this concept to a 4x1 multiplexer, moving towards the case where we can implement any required multiplexer. So, we will start with the basic multiplexer, then we will see how we can go for a larger scaled version of the multiplexer, then we will see the applications of multiplexer. So, first of all, what is a multiplexer? To understand this better, let us discuss about movies. If you see, you have single screen theater, you have multiplex. What is the difference between a single screen theater and a multiplex? Single screen theater, there is only one screen, whereas multiplex, there are many screens inside a single building. Okay, fine. So, if you understand that, this concept you can easily understand. So, multiplex means you have so many screens, so many movies running simultaneously in a single building. Okay. So, likewise, here the multiplexer, what you can easily understand is, it is simply understand like this. There are many signals, right? Fine, which can be multiplexed into a single signal. In this case, in a 2x1 mux, two input signals are multiplexed into a single signal. So, if you have a multiplex with 4 screens, then 4 signals in a single building. Okay. Now, a user will select which screen or which movie a user want to see. Okay, fine. So, there is some selection that is required in the case of a multiplex. Likewise, in the case of multiplexer, the electronic component multiplexer, we have selection lines. Okay, fine. So, suppose if there are only 2 signals, like in this case there are only 2 signals, then the choice that the user has to make is very simple. Okay, fine. That is, either you pass D0 to output or we pass D1 to output. Fine. Now, when the choice is very simple, the number of bits required to implement that choice is also very less. Okay. So, in this case, 1 bit of information is sufficient for the selection lines. So, now let us see the general definition for the multiplexer. Okay, the general definition for the multiplexer is also called as mux. Okay, fine. So, it is a circuit that has data inputs. Now, in this case, these are your data inputs, okay, D0 and D1. It has selection lines, okay. So, here S is your selection lines and one output. So, here I would like to emphasize that a multiplexer has only one output, irrespective of number of inputs, irrespective of number of selection lines, the output is always 1. To understand this, okay, let us once again go back and discuss about multiplex, where multiple movies are running in a single building because of multiple screens. So, even if you have 4 screens, they are in a single building. Fine. Or even if you have 8 screens, still there is a single building. A user is going to only one particular building, right, to watch any of the 8 movies. Fine. So, understanding this way, we can be sure that the output of a mux is always one line. Inputs, okay, can be more than one line. Selection line can be more than one line. Okay. So, in general, if you have n selection lines, then we have 2 power n inputs and output is always 1. Okay. So, Let us take one simple example where n is 1. So when n is 1, 2 power n is 2. So the possible mux that you can have is 2:1 mux. Okay, 2:1 mux. What does it mean? 2:1 mux means here 2 is the number of inputs and 1 is the number of outputs. Okay, fine. So always here this will not change for any multiplexer. Output is only one line. Okay, so you can have 2:1, you can have 4:1, you can have 8:1, you can have 16:1, you can have, okay, 2:1, we can have 4:1, we can have 8:1, we can have 16:1. This one I hope everyone understood, because output you have only one line. Then why this 2, 4, 8, 16? Because it is in the power of 2. Okay, the number of inputs are always in the power of 2. Fine. So this is the circuit symbol of multiplexer. Okay, and as discussed, S in this case is your selection line and D0, D1 are the two inputs. Okay, fine. D0, D1 are the inputs. Clear? And Y is the output and Y is the output. Okay, now the truth table is very simple. Fine. That is, if selection line is 0, I repeat, if selection line is 0, then Y is simply equal to D0. So now you can view this as a switch. Okay, fine. That is a switch which either connects D0 to Y or it connects D1 to Y. If the value of this bit is 0, it connects D0 to Y. Suppose if we give a 1 here, then it connects D1 to Y. Okay, so here we can see when we give 1, output is D1. So direct, it's as good as we have a direct connection between D0 and Y. Okay, fine. And earlier case also we have seen, when S is 0, what is the situation? D0 is connected to Y. So here when S is 0, D0 is connected to Y, which means Y is simply equal to D0. Very simple truth table. So now here what you can do is, based on the truth table, directly we can get the Boolean expression of the output Y. Okay, so now once we get the Boolean expression, it is easy to construct the circuit based on that Boolean expression. Fine. So how we can get the expression for Y? Here we have 0. So trick is this: if you have 0, you will take the variable in its complement form. If you have 1, you will take the variable in its true form. Complement form means when you have S, you will take S bar. Okay, right, that is complement form. True form means if you have S, we will take S. So here what is the situation? One case is this: 0 D0. So S bar D0. Okay, S bar into D0. Okay, so in this case we have Y is equals to D0 into S bar, and then here now in this case we will have D1 into S. Okay, D1 into S. Fine. You can write S into D1, D1 into S. Okay, right, both are accepted. So what is the expression you will have here? So first, for this you have D0 into S bar corresponding to this first row. Corresponding to the second row we have D1 into S. Okay, D1 into S. Now this is the expression for Y. Once we have the expression for Y, based on this expression we can construct the circuit diagram. Okay, so let us see how we can do that in the next slide. So this is the 2x1 multiplexer also known as mux, and this is the same expression which we have seen in the previous slide. Now based on this, how we can construct circuit? Okay, very simple. We need S bar. Fine. how we can get S bar? How can we get S bar? That is, pass S to a NOT gate, output of NOT gate is S bar. Okay, fine. Then D naught into S bar you can get here as the output of the AND gate, D naught into S bar. So this term complete D naught into S bar, we get the signal here. Fine. So AND gate for multiplication, OR gate for addition. Now again here we have multiplication between D1 and S. Okay. So here D1 and S, right? Multiplication means AND gate, D1 S. Okay. Now addition means we have seen OR gate. So what we need to do, take the OR of D naught S bar which we are connecting here and then D1 S, right? Then we get the final expression which is Y. So circuit very simple. Fine. Now let us go back and see the general pattern that we have seen here. Okay, that is, now concept is very simple, right? 2 by 1 mux, 2 inputs, 1 output. Okay, in this case n is 1, so number of selection lines is 1. Based on this we can construct the table, right? Fine. And based on the table we can get the Boolean expression. From the Boolean expression we can get the circuit diagram. We have seen all this logically. Now what we will do is, let us generalize, okay, so that students will be able to implement a mux of any size. Now the central idea will be same. Okay, the central idea that we have seen for 2 by 1 mux is sufficient for mux of larger sizes also. So as a practice of that, let us go for 4 by 1 multiplexer. Okay, so let us go for 4 by 1 multiplexer. So now 4 by 1 multiplexer, obviously what is the general situation? 2 power n inputs. Okay, we have seen this in the previous slide. We have 2 power n inputs and then we have n selection lines and we have always one output, right? So here the second case, earlier we have seen first case when n is 1 selection lines, 1 selection line. Now n is 2, so 2 selection lines. Okay, so n is 2, so 2 power 2 will be 4. Fine. So the number of inputs will be 4 will be the number of inputs, right? 4 will be the number of inputs. So here you have 4 inputs, right? 1 output, hence the name of the mux 4:1. It doesn't matter how many selection lines are there. The name of the mux is based on the number of inputs and number of outputs alone. Okay, 8 inputs, 1 output, 8:1 mux or 8:1 multiplexer. Okay, now what we will do is, we will discuss what should be the output, fine, in terms of the inputs and selection lines. So when selection lines both are zeros, then we pass on the first one to the output, D0 we pass to the output. Okay, right? For the case when selection lines are 0, 1, fine. So what are the 4 possibilities of selection lines? 2 bits possibilities are 0, 0, 0, 1, 1, 0, 1, 1. Okay, so the way we design this concept is 4 possibilities. Based on the 4 possible values, we can have 4 possible connections of the input to the output. Means when we have 0, 0, D0 is connected to output. When S1, S0 both are 0, zeros, then D0 is connected to output. When you have 0, 1, then D1 is connected to output. Fine. Then when we have 1 0, then D2 is connected to output. When we have 1 1, D3 is connected to output. Simple. Okay. So truth table is also very simple. Now what we need to do is, we need to draw the circuit diagram based on this. Okay. So concept is very much similar as that of a 2 by 1 mux. What did we do for a 2 by 1 mux? We have taken circuit symbol, from circuit symbol truth table, from truth table the circuit diagram. We are going to follow the same process here. So now how can we get the expression for output? Now the expression for output will be simply output is equals to, okay, let me write here, output will be S1 bar, S0 bar, S1 bar, S0 bar into D0, okay, plus S1 bar, okay, y S0 bar, y S1 bar, S0 bar into D0, similar to previous situation, okay. That is, because we have a 0 here, we will take S bar, okay, we will take S1 bar because we have a 0 there. Again we have a 0 here, so we will take S0 bar, the variable in its complement form. Then we have D0, right? So the D0 as it is we will take, okay. So again you have a 0 here, so now you will take S1 bar. We have a 1 here, so we will take S0. Fine. Then D1. And what will be the third one? The third one will be S1 into S0 bar. S1 into S0, S1 into S0 bar into, right, S1 into S0 bar into D2. Okay. Then last one will be 1 1 D3. So S1 S0 in its true form, S1 S0 and then D3, right. So this is the expression for output. Now based on this, easily we can construct the circuit diagram. How? Here in this case, S1 bar, S0 bar, D0. For this complements of S1 bar, S0 bar, to get these complements we can use NOT gates. So first we are taking NOT gate here, okay, we are taking a NOT gate here, fine, to get the S1 bar. Then obviously to get the S0 bar, one more NOT gate we are taking here to get the S0 bar. So the first, the rounded one here, fine, this is the first product that we have. So how to get the product? We have seen in the previous case, AND gate is going to give us the product. AND gate is going to give us the product. So product of what? Product of S1 bar, S0 bar, D0. Okay. So D0, first signal we are giving here. Second signal, if this is S1, the output of NOT gate, here you will get S1 bar. Okay, here we are going to get S1 bar. So that S1 bar we are connecting here. Then if this is S0, then you know very well output we are going to get S0 bar. So that S0 bar we are connecting here. Simple. Okay. So one AND gate for the first product term. Another AND gate, likewise another AND gate for the second product term. Another AND gate, okay, for the second product term. Third AND gate for, okay, the third AND gate for the third product term, okay, the third AND gate for the third product term, and final AND gate final AND gate for the fourth product term. Simple, right? Now in between the product terms you have plus, which is the gate which will implement the product, which will indicate the addition. It is the OR gate. So all these outputs we are simply connecting to the OR gate. Okay, all these outputs we are simply connecting to the OR gate. Fine. Okay, so I hope now students will be able to construct any given multiplexer. Fine. Okay, so now let us go for the applications of multiplexer. Here, now wherever you can combine into a single line, like, okay, we have seen general usage, multiplex, we are combining screens into a single building. Fine. So wherever we can combine multiple lines of data into a single line, wherever such a requirement we have, there we have the application of multiplexer. Okay. So to combine, for example, in data communication systems, to combine multiple voice signals onto a single communication channel. Okay, fine. So your telephone system, what you can have so many lines, clear, and you want to communicate to a single person, suppose, then what you can have a multiplexer like of arrangement, where based on the selection lines, any of the line is connected to the single output. Okay, so here onto a single, this is valid only for the case when you are multiplexing onto a single line. Okay, then we can have data from various sources onto a shared communication line. Fine, right? It could be voice signals. You are multiplexing all the voice signal onto a single line. Okay, for example, large signal transmission, or you want to switch between various signals, we can have the application of multiplexer. Then next, in digital signal processing, again to select different data paths for processing, we have seen that multiplexer is like a switch, either it connects D0 or D1 to the output. Fine. So path selection, okay, we can use multiplexer for path selections. Then control systems, to route signals from different sensors to a central controller. Okay, whenever we have the outputs from a sensor, and based on the output of sensor, for example, first case you want to send the temperature signal to the output, to the controller. Okay, another case you want to send, say, the humidity signal to the controller. Fine, there again you can have the application of your multiplexer. Then in video and audio processing, okay, fine, to combine different signals onto a common transmission line, right? Fine, we can again use the multiplexer. Then in sensor networks, to select readings from various sensors for further processing. Okay, fine. So these are the applications of multiplexer. In simple terms, a student has to visualize based on the requirement. Fine, whenever he has to say select a particular signal out of many signals, or a student has to multiplex so many signals onto a single line, then there a student can use application of the multiplexer. Okay, fine. So in today's session we have seen what is a multiplexer. We started with 2x1 multiplexer, we have extended that idea to 4x1 multiplexer, and the same concept is valid for 8x1 multiplexer or 16x1 multiplexer. This central idea is sufficient. Students can go ahead and build those multiplexers also, and depending on the practical requirement, the student will select the size of the multiplexer. And we have seen the applications of multiplexer. So that's all for today's session. Thank you so much.